We've taken a look at slope-intercept form of the equation of a line and the standard form of the equation of a line. We've learned how to graph both of those. Today we are going to take a look at one more type of equation for a line, and this is called the point-slope form. Now the point-slope form of the equation of a line can be written using a point x1, y1 and the slope m. Now the format or the template that it follows goes like this: y minus y1 equals m times x minus x1. And we substitute in the values y1 for the point, m for the slope, and x1 for the point. The other two x's and y's, or I should say the other two variables x and y, are a part of that equation. So let's get a practice here. The equation of a line equation of a line containing the point 3, -7 and a slope of 2 can be written like this: y minus a -7 is equal to my slope 2 times x minus my x-coordinate of 3. Now we do have a minus a negative, so we're actually going to change that because we know minus a negative is really just plus. So here is our point-slope form of the equation of this line that contains the point 3, -7 and has a slope of 2. Next piece of terminology that we're going to talk about today is called a piecewise function. Now, if you break down that word piecewise, you can see that it has the word piece in it. And what it is it's just piecing together multiple functions over different domains or different intervals. So here is our function. It's going to take on three forms. It's going to take on the graph of y equals -1, where x is less than 0. It's going to take on the graph of y equals x squared between 0 and 2 on the x-axis. And it's going to take on the form of -x plus 2, where x is greater than 2. So past the comma here, over here on the right-hand side, these are the graphed domains, or the intervals in which you'll see these graphs. And so we've pieced all of these together to form what we call a piecewise function. The graph or the function changes based on the domain or the interval over which it's graphed. All right, let's jump into some examples for today. We have a spring. It's 23 inches long when it has a 3-pound weight attached to it. The length increases 3 inches with each additional pound of weight added. This is a constant increase situation, also known as a linear function. We want to write a formula that relates the spring length L and the weight W in the point-slope form. So we know that the length of this spring is a function of the weight, W, L. These are our relations on this coordinate. So we have one of the relations. We have when a 3-pound weight is on this spring, we know that it is 23 inches long. We also know the slope, or the constant rate of change for this problem. The constant rate of change, or the slope here, is 3 inches for each additional pound. So here we have a point that exists on this relation, and we have the slope. So we're going to write this in point-slope form. And it will go like this: y minus my y-coordinate here, 23, is equal to the slope, 3, times x minus my x-coordinate, which is 3. And here is the equation for, or the formula for, this linear function written in point-slope form. Now you can see part B really wants me to change this to write this into slope-intercept form. So in order to write this in slope-intercept form, we are going to get y by itself. In order to do that, we are going to distribute our 3 into the parentheses. So I'll have y minus 23 is equal to 3x minus 9. And now we're going to add 23 over to the other side. Oops. So that gives us the function y equals 3x, and then I have a -9 plus that 23, which is going to give me positive 14. All right, so here is the slope-intercept form, or equivalent of the point-slope form that we started off by writing. Next up, let's get a little picture of what's going on here. So we can use our slope-intercept form. Our y-intercept is 14. We can see we have a constant rate of change of 3. So as we go over 1, we're going to come up 3 pounds. over 1 up 3 pounds, over 1 up 3 pounds, so on and so forth. So right now it looks like a discrete graph. However, it is possible for this to be a continuous graph because it's possible for me to have some other increment other than just a 3-pound weight added to it. But here you go, there's the graph of that situation. All right, let's check in with example 2. It says to use the point slope form to write the equation of a line that passes through these 2 points, 6, 4, and 15, -2. So there's one additional step that we need to do first before we write this point slope form. We have obviously 2 points that it passes through, but we don't have the slope. So we need to find the slope. So finding slope using our formula, which says the change in the y coordinates divided by the change in the x coordinates. That will simplify to our -6 over 9, which can be reduced to -2/3. So once we've found our slope, it doesn't matter which point we choose. We can choose either one, and we can write point slope form. So let's go ahead and do that. We're going to say y minus 4 is equal to my slope of -2/3 x minus 6. Now, we're going to now change this to slope-intercept form. So converting from point slope form to slope-intercept form, you saw us do that in the previous problem. We're going to distribute in our -2/3, so we end up with -2/3 x plus 4. And now we have to add that 4 to both sides, and that's going to give us the equation y equals -2/3 x plus 8. And so we can see our slope is -2/3 and our y-intercept is +8. All right, example 3 says, suppose that we know a formula for relating blood pressure and age. We know that it's linear and that the normal blood pressure for a 20-year-old is 110. And for the normal blood pressure for a 60-year-old is 130. We want to construct a formula, or in this case a linear relationship, in which the blood pressure B is a function of the age A. So that means B is going to be dependent on our age. All right, so we have a couple of relations here already. We have a blood pressure of 110 for a 20-year-old, and we have the normal blood pressure for a 60-year-old of 130. So just like in our previous problem, we have 2 points that exist on this linear relationship, but we first need to find the slope. So taking the difference in the y's and dividing by the difference in the x's, I will end up with 20 over 40, which reduces to 1/2. So there's the slope between those 2 points. Next, I can choose either of these 2 points, it doesn't matter which one, to write my point slope form. So we're going to say y minus 110 is equal to my slope of 1/2 times x minus 20. And there is a model, a linear model, that relates blood pressure and age. All right, in our final example for today, we're going to talk about a piecewise function. Now, a piecewise function often looks like segments on, or broken up pieces on a graph, okay? So here's Franny. She's going to take a bike trip. The graph below depicts her traveling distance over a period of time. We want to write a piecewise linear function for the first 3 segments of Franny's trips. All right, so what that means is we are going to write 3 linear equations for segment 1, segment 2, and segment 3 of her trips. Now, what you notice here, if we just zoom in here on segment 1, is that this is really just a line segment over a specific interval. And it looks like it goes from the interval of 0 all the way out here to, let's just call that 40. All right? Now, I can write the equation of this line if I have 2 points, because I can find the slope, and I see that it passes through the origin 0 here. So let's just find the slope of this line. Well, remember, slope is change in y over the change in x. So going from these 2 points here, I can see that the change in y looks like it's about going from 0 to, let's call it 6, all right? So there's my slope, there's my change in y. Over my change in x, looks like it goes from 0 all the way out here to 40, so 6 over 40, and we can reduce that down to 3/20ths. All right, so there's the slope of this line here, and it passes through the origin, which means my y-intercept is 0. So the equation of this line will look like this. Y equals 3/20ths x. Now, we have to define the domain over which it's graphed. It's only going to be graphed between where x is 0 but less than 40. All right, so there is our first segment's linear equation. Our next segment, if we take a look at that a little bit closely, we can see that this is just a horizontal line. And that horizontal line, remember, takes on the equation of y equals, and it's whatever those y coordinates are. Well, it looks like our y coordinates here are going to be the same as our last y coordinate, which was just y equals 6. So here's our second equation, y equals 6, and it's going to be graphed over the domain from where x goes from 40 to where x goes to 60. So we put our little domain restrictions on it, just like that. All right, finally, we want to graph the equation for, or write the equation for the segment here, segment number 3. So this looks like it's at 60 over and 6 up, and it's going to go all the way up here to this point, which is 90 over and 12 up. So we have 2 points. We want to find the slope, and then we can use point slope form to write the equation of that line. So let's start off by finding the slope. We have 12 minus 6 divided by 90 minus 60. That's going to come out to be 6 over 30, which is 1/5. All right, once we have our slope, we are now going to put it into point slope form by choosing either of these 2 points. So we have y equals, let's put it in point slope form first here. So we have y minus y1 is equal to 1/5, my slope, times x minus x1. All right, now, since I don't have this solved for y just yet, I'm actually going to bump this 6 over here to the other side so that I have it set equal to y. So this is going to give me 1/5 times the quantity x minus 60 plus 6. Now this interval is going to be where x is going to be greater than or equal to 60 but less than or equal to 90. All right, so those are 3 linear equations for the first 3 segments describing Franny's